All right. Hello. Hello. I'd like to call this colloquium to attention. Gavel. So I'm Bob Continetti. I still sometimes come to chemistry and biochemistry, and it's a pleasure today to come to introduce my colleague Wei Xiong. So Wei's a scientific relative of mine. He's a great grandson of Y.T. Lee, my PhD advisor, and so we have a familial relationship. He did his PhD with Martin Zanni, who I think many people would say is one of Dan Newmark's most productive PhD students at the University of Wisconsin, where he learned about 2D IR and some frequency generation spectroscopy. And then he went on to a very successful postdoc with Margaret Murnane, where he learned about X-ray, tabletop X-ray studies of nanoparticles. So a very strong preparation in the really cutting edges of laser spectroscopy, laser science here at the beginning of this century. Since coming here to UCSD in 2014, so this is after 5 years, is a very important talk for somebody like Wei. He comes to this talk today with a very impressive publication record. I'm sure he will tell you about highlights of that today, but also an impressive record of awards. DARPA Young Faculty Award, AFOSR Young Investigator Program Award, DARPA Directors Fellow, NSF Career Award, and finally this year the American Chemical Society Journal of Physical Chemistry / Physical Chemistry Division Lectureship Award, where he's gone out to different institutions and as a young scientist talking about his exciting new research. So not wanting to take away any time from Wei, I would like to call you up, Wei, and please tell us about the work you've done here at UCSD.
All right, thank you, Bob. Thank you for the nice introduction. I'd like to just first apologize a little bit. I got a cold last week, so I try to control it, but I might cough a little bit. Okay, but I will try to excite you by the science. That is telling you something we did in the past 3 years about that is some hidden physics we find in molecular materials by using nonlinear spectroscopy. So overview about my group. My group really focused on applying nonlinear photonic techniques onto molecular science and try to understand some hidden physics of those molecules and molecular materials. And one example is we demonstrated that by adding a time domain into SFG, we can follow ultra-fast charge transfer at interfaces, which is what I talked about last time. And we keep working on this direction by basically showing that there is a direct charge transfer can happen at organic and metal interfaces, but also we developed this technique that allows us to resolve phase of the SFG spectrum. If you came to Cliff talk yesterday, you know that it's important to measure phase of SFG. By doing that, we can measure the real and imagined part of the spectrum and then follow their dynamics. You see their dynamics is different. That is because the real part actually encodes the electronic dynamics, where the imagined part is safe to say is mostly dominated by the vibrational dynamics. So now we can separate them and really figure out the details of charge transfer in those systems. And we now look forward to apply those techniques into systems like photoelectrochemistry cells, as well as these novel 2D valve materials. Those are some really interesting material. By shining light onto it, you can just generate direction currents onto those materials. And this work has been done by my a former graduate student, Yingmin Li, who graduated recently, and taken over by this new student, Cheng Lai, who's in the audience. So today I'm going to focus on these two new topics that I didn't talk about last time. The first one is using two-dimensional infrared spectroscopy to study molecular system that is strongly coupled with photon cavity mode, or the so-called molecular vibrational polaritrons. So if you remember what Howell talked about a year ago, you might know this concept about molecular polaritrons. But basically, polaritrons are hybridization between molecules and between photons. Okay? So we all are very familiar with the idea about hybridization that occurs in systems like J aggregates, excuse me, beta sheets, and also molecular orbital theory. All right? So they all have some common ground there. That is, the individual units are getting so close to each other they actually have a spatial overlap that make their orbital also strongly overlap with each other. Therefore, making them strongly have a spatial overlap and coupling term in the Hamiltonian. Therefore, the Hamiltonian, when you diagonalize them, you find the molecular orbital needs to be renormalized and redistributed from those new eigenstates. So as a result, the excitation of the orbital itself is delocalized, and usually in spectroscopy, you see the signature of double peaks. But the key here is a really good spatial overlap between orbitals. So for polariton, it's the same idea, except now we need to replace one of the molecular resonance with a cavity resonance. We need to first make a cavity resonance. The easiest way to make cavity resonance is by putting two partial reflective mirror together to form this so-called fibropolar cavity. The criteria is that we need to make the distance between the two mirrors to be L, which is half integer of the wavelengths that you are interested in. For example, if you're interested in molecular vibrational mode, then which absorb around 5 micron, then it means that the cavity thickness can be 2.5 micron, 5 micron, 10 micron, 25 micron, so on and so forth. Those are all allowed cavity mode to couple to the vibrational mode. Okay, if you measure a FTR spectrum, you will find this Lorentzian type of line shape. But more importantly, in the time domain, if you measure free induction decay, you see this exponential decay curve indicating how long the photon can be trapped inside of the cavity. Now, let's imagine just putting one molecule inside of the cavity. What the molecule going to do is going to basically driven by this electromagnetic field inside the cavity and then just oscillate. And then it's going to emit its own electromagnetic field, right? As a result, it's going to add a dip to this transition mode. It's just like an absorption. More importantly, in the time domain, what we will see is in the vibrational mode and cavity mode, they all just, after excitation, they just exponentially decay. There's no energy exchange. This is just a typical weak coupling regime that we do every day on our UAVs, on our FTIR. This is not strong coupling. Of course, this is not strong coupling because there is not a good spatial overlap. Why? What is the size of a molecule? A cubic of angstrom. What I told you about the size of the cavity, the length is on the order of micron. So we're talking about a cavity mode that is on the order of cubic of micron. So there's a majestic energy, volume mismatch between the cavity and the vibrational mode. Of course, they won't strong couple to each other. So one way to make them strong couple is just to make you can either make the vibrational mode to be larger or make the cavity mode to be smaller. And people have tried to make the cavity mode to be smaller by doing a lot of nano engineering, but so far it is still a very challenging field. So the easy route is to actually just by putting a lot of molecules inside of the cavity. By doing that, this collective motion of molecular vibrations would somehow form this super radiant state so that it would form a large delocalized macroscopic polarization where overall this macroscopic polarization would have a volume that match with the cavity volume. And in this way, the cavity now can actually feel this macroscopic polarization. And as a result, this cavity mode would split into two separate peaks, okay? And those two separate peaks are characterized by their separation that is referred as the so-called Rabi splitting, where the lower frequency peak are referred as the lower polariton and the higher frequency peak are referred as upper polariton. But most importantly is what you see in the time domain. What you will see is actually after we put initial energy into the vibrational mode, we will see the energy actually shuffle between the vibrational mode and the cavity mode back and forth several times before both of them decay away. So within the lifetime of either of the mode, we really cannot say where we put the energy in. That is why we cannot use vibrational mode or cavity mode as an eigenstate anymore, and we need to use the polariton mode as eigenstate. So there's strong enough coupling, we really cannot use the original basis set anymore. Okay? So what I said here in the time domain can be summarized in the frequency domain as well. That is, the Rabi splitting needs to be larger than the full width half max of either the matter transition or the cavity transition. This is a more straightforward way to quantify if you are in the strong coupling regime or not. But also, this Rabi splitting is proportional to the coupling strength. and which the coupling strength is depend on how many molecules you put in. That can be summarized by the square root of concentration, an important relation that we need to come back later. But based on this theoretical picture, I would argue this is not the typical hybridization that we see. This is a hybridization between macroscopic object, that is the photon cavity mode, and microscope, a collection of microscopic objects. Those are the individual molecular vibrations. So by coupling photon and molecule together, we might expect to see some interesting photonic and molecular behaviors. And that is what I'm going to talk about today. There is already an interesting paper published by this guy in France, Thomas Eberson, where what he showed is by putting some reactants inside of the cavity, even without any photon excitations, they, they can actually change the reaction selectivities by coupling to the cavity mode. It's a really interesting result. Nobody really understands, but this is, and it's only published like early this year. So this is why we are interested in this field. What we are interested is to understand the novel chemical physics and also photonic properties. So right after we see the first example from Eberson's group and also Simpkins' group in 2015, we step into the field with our own uniqueness, that is nonlinear spectroscopy. None of them do this. We choose our favorite molecule, tungsten carbonyl, because it has a really strong transition dipole moment. I just learned about 2 weeks ago, tungsten carbonyl is also good at some chemistry. I always thought it's just a hydrogen atom in infrared spectroscopy. Anyhow, if we prepare this highly concentrated solution and put it into the cavity, we would generate this proton mode that is separated about 40 wave number, way much larger than the with half max of the vibrational mode and of the cavity mode. So we know it's in the strong coupling regime. Before I move on, I want to give molecular vibrational proton an acronym because it's too long for me to say. So I call it MVP, with apparently the hope that they could be the MVP like those NBA players. So those are the time where I still follow NBA. Anyhow, just one slide about theory. The way to think about it in theory is just a matrix to diagonalize it. Basically, in this cavity, we have one cavity mode where we have n vibrational mode that all can couple to the same cavity mode. But between those vibration modes, they don't couple to each other. You can diagonalize this matrix. What you find is there's totally n plus 1 new eigenstate. But among them, only 2 of them, that is the lower proton and upper proton, has the photonic or the cavity wave function in. That makes them to be the bright state, which we can actually see. That's why you see 2 peaks in the linear spectrum. Whereas the rest of them, that n-1, are the so-called dark state. They have the same energy as the uncoupled molecule, and they should not be seen in the linear spectrum. However, the n that we talk about is not 10. It's about 10 to the 5th to 10 to the 10th. It's a lot. It's really dependent on the size of the cavity, right? So it's not a small number, and those dark modes could also influence the dynamics of proton, which I'll come back later. In terms of technique, we use pump probe spectroscopy, where we send an infrared pump to excite the system, and then follow up with the infrared probe to basically measure the probe spectrum. Here is one example where we can measure the probe transmission spectrum. You see this is the characteristic proton transmissions, but even with either the pump to be on or pump to be blocked, you can see that we can modulate the transmission spectrum of the probe. Okay, if we take the difference, you got the pump probe spectrum. We see a large absorptive feature, which I will come back later. Another technique that we use for this audience, I believe a lot of you are familiar with, are 2DR. So this is basically a version 2 of pump probe, I would say, because we can actually resolve the quantum state along the pump axis as well. The way to do the experiment is to actually sending in 3 infrared pump pulses where we create a vibrational coherence in the first, after the first light matter interaction, let it evolve over T1 time, and then terminate this coherence with a population state and wait for a T2 time. This is where we allow those vibration modes to actually evolve, and then retag this vibration mode by another coherence again with a probe pulse, and then measure the immediate probe signal. Okay, so we usually call it a vibrational correlation map, because I can show you why that we call this, taking the example as the polariton system I'm focusing today, where you have a lower polariton and upper polariton, totally two new eigenstates, the easiest system that you can imagine. Right? So in the 2D experiment, what happened is if we initially pump at the upper polariton, so we excite at this frequency, we're going to get a response. And then if this energy retain inside of the upper polariton, by the time we probe it, it's going to absorb at this frequency. So you will have a peak showing up along the diagonal. This corresponds to the diagonal peak. You can have two diagonal peaks correspond to the two linear spectral peaks that correspond to the upper polariton and lower polariton peaks. However, if we put initial energy into the upper polariton, but after the waiting time, the energy actually transfer to the lower polariton, then instead of seeing a peak at here, we are going to see a peak at here. They would occur as a cross peak. Basically, this is a way that we tell if molecules or quantum states are coupled to each other, and also there's energy transfers between them. Give you a realistic example. This is one of the 2D spectrum we collected on the polariton system. You can clearly see we can draw the same type of box feature with upper polariton diagonal peak, lower polariton diagonal peak. But most importantly, we see two strong cross peaks indicating the strong interaction between them. And this is just like NMR, 2D NMR that many of you guys are also familiar with. So now I want to go into the science to tell you four different interesting phenomena that we found using those techniques by studying polaritons. This work are mostly led by my student Wei Xiong, except the last one is led by my former student Jiaxi, and Mo and Li Ying just recently joined to the project and this interesting journey. So coming back to this pump probe data that I showed you before, as I showed you, as we block or unblock the pump, we can modulate the probe transmission spectrum. With this, we take the difference, it gives us this purely absorptive type of line-shaped pump probe signal. We call it polariton bleach. What we find is very interesting is when my students just keep every parameter to be the same, but just changing the cavity thickness, what he found is that by reducing the cavity thickness, okay, making the cavity to be smaller and smaller, we got larger and larger nonlinear responses. So this is abnormal because typical trained nonlinear spectroscopy, we all know that the linear spectrum and the third order signal, they are proportional to the sample concentration and also the sample thickness. So if we take the ratio, they should cancel out. However, this is clearly not the case. But from the other way that you think about it is, any nonlinear spectroscopy are measuring the molecular anharmonicity, which is a property of the potential energy of the molecule. So really, if you want to change that, I would argue I should go to the wet lab and do some chemistry, change the molecular structure. But here, we are not changing that. The only thing we are changing is actually just the volume of the cavity. And the reason we can do that is because of now, you need to think this excitation is not a microscopic excitation anymore. It's actually a macroscopic polariton excitation because we hybridize both the macroscopic cavity mode with the microscopic vibrational mode. And the detailed proposed mechanism is the following here. Let's imagine with the two cases where we have a cavity size of 25 micron and a cavity size with 12 micron. In those experiments, we keep the molecular concentration to be the same, but we basically simply just changing the cavity thickness. By doing that, we are basically changing the total number of molecules or molecular wave function available inside of the cavity. And when we do the pump probe experiment, we send in a certain amount of photon into those cavities. That determines how many number of polaritons that we can generate. So given if we can generate the same number amount of polaritons, in this case, we have more wave function to generate polariton. Therefore, each molecular wave function would contribute less. Whereas in this case, those molecular wave function, each of them would contribute more to the polariton formation. Therefore, this case is more close to the saturation limit. We believe that is contributing to the enhanced nonlinearity. Of course, this is just a hypothesis, but the key, what we try to deliver here is what matters is the total number of molecules inside of the cavity to form this polariton. okay? And we can test that by basically keeping the cavity thickness to be the same, but just try to reduce the number of molecules by reducing the concentration. There's a caveat because of the Rabi splitting is also a function of the concentration, but that's the best control experiment we can think of. What we found is also very stunning that by reducing the concentration, okay, we can actually see the nonlinear signal increase for both if we excite on the upper proton side and lower proton side. This further support this proposed mechanism and the idea that this proton is a delocalized macroscopic vibrational polarization. And really what matters for those optical nonlinearity is the total number of molecules involved in generating those protons. But practically what we found is very interesting is if we want, we might be able to actually develop those protons into an ultra-fast optical modulator to turn on and turn off its transmission at certain wave, light regime, and also control its ability by just control those macroscopic parameters without going to the wet lab, which I'm not really good at. All right, so we are also very interested about the physics behind this type of phenomenon. So we further carry some 2D experiment. Using 2D experiment, we basically disentangle this simple pump probe experiment along the pump frequency so we can resolve how the system evolves if we just pump the upper proton side or lower proton side. For example, we can take a cut at the upper proton side and follow its dynamics. So this is just like a upper proton specific pump probe experiment. What we find is those beautiful oscillations, all right? And this oscillation has a period about 0.8 picosecond. That corresponds to a frequency of 40 wave number. If you remember the Rabi splitting I showed you before is also about 40 wave number, 38 wave number we did with FTIR. So what that suggests is the origin of this bleach type of signal are actually coherent. It is coming from this Rabi oscillation between the lower proton and upper proton. What is important is, if those of you do not know what is coherence, but there are some buzzwords you know that if you can create coherence or superposition state, then quantum computing is available, okay? So we might be able to further develop it into a qubit for a new platform for quantum simulation. There's a long way I want to give you, a caveat there. There's a long way to go, but I think there's some potential there. All right, so move on to the next interesting phenomenon, hot vibrational dynamics. So now I'm moving on to those pump probe scans, but at a longer time delay. Previously, I showed you the pump probe where that the two pulses are really close to each other within the lifetime of the proton. Now, after I pump the vibration, the proton, I let the probe to wait for a certain time that is longer than the lifetime of a proton. Okay, so the proton would actually relax into something else. The something else is the so-called dark state. That's where dark state become important. As a result, the spectrum also looks very different. Here is the pump probe spectrum. You see on the upper proton side, it's not a absorptive shape anymore. It's a derivative shape, where you can also see a small derivative shape on the lower proton side, but mostly the lower proton, excuse me, proton side is still dominated by this strong absorptive peak. All right, so this derivative shape can be explained by the so-called Rabi splitting contraction. What it is in the pump probe experiment, I'm removing some of the population from ground state to the excited state, all right? And then because the Rabi splitting is proportional to the concentration of molecule inside the cavity, then I'm basically optically reducing the molecular concentration in the cavity now. So I can shrink the cavity, the Rabi splitting here. As a result, the lower proton would shift up and upper proton would shift down. And if we do a simulation, you can see that both peaks getting close to each other, and then if we take the difference for the pump probe, we get this kind of derivative shape. So that matches with the derivative shape on this side really, really well, and also this side kind of well. But of course, this is now the full story. There is a large absorptive peak that we haven't taken into account. So what is that? that is indeed due to a excited state vibration level 1 to 2 transition of the dark mode. So the dark mode, I told you, is dark, but it's dark for its fundamental transition. Its overtone transition happened right around 1960, so then it can borrow the oscillator strength from the lower polariton and then just become visible and generate a large transient absorption signal through the lower polariton. And that we can also simulate it while using available model. So this absorption peak then become a really interesting and useful parameter here, because by using that, we can actually follow how fast this first excited state being populated after polariton being transferred. Because those dark modes are also important to trace in the polariton system. People believe they are involved in polariton chemistry. And again, 2DR basically just support what we said. We also see these strong absorptive peaks on the lower polariton side due to this excited state absorption of dark state. But basically, to summarize, the kinetics about polariton are like this. So after I initially excite those polariton state, they would have a short lifetime and interact with each other, generating this large spike. This large spike lasts about maybe 5 picoseconds, really depend on the lifetime of the cavity mode. But then it would relax to the dark mode and then populate this excited state absorption of dark mode, and then causing this growth of this dynamic spike again. Okay? So, however, you might have the question that I have as well. Then if that's the case, after the polariton relax, it immediately jump to the dark mode for the excited state. I would expect to see these dynamics to just jump up right away instead of having a really, really slow rise up. So it suggests there might be some intermediate state. And that's what we found is interesting. To further understand what could be the intermediate state, we perform 2DR spectroscopy. Using 2DR, again, we can basically resolve the kinetics of different channels. For example, this peak represent by putting energy only into the upper polariton state, how it's gonna relax to the dark mode. While this peak represent by putting energy only into the lower polariton state, how it's gonna relax to the dark, lower polariton, how it's gonna relax to a dark state. So we basically take those 2DR spectrum at a series of T2 time delay to follow the dynamics. The T2 dynamic is just a waiting time in a typical pump probe experiment, where that if we integrate those spectral peaks and just plot them as a T2, you see for the upper polariton case, it just simply decay. So we take those spectrum after polariton relaxation, so you don't see this spike anymore. However, for the lower polariton, we see that it's actually delayed rise. It doesn't rise until 15 picoseconds. Okay? What it suggests is the upper polariton and lower polariton dynamics are different. Only lower polariton actually go through this intermediate state. And what is this intermediate state? We scratch our head for a long time until that I found a paper by Ted Havel published in 95, where I'm still in elementary school, that show for tungsten Hessian carbonyl, its vibrational dynamics actually are dependent on how the pump wavelengths, the energy of the pump beam. He showed that if he has the pump trained to 1968, very close to 1963 of our lower polariton transition, the molecule would preferentially be excited into the second excited state and third excited state, skipping the first excited state. So that gives us a huge hint and make us believe what happened during this lower polariton relaxation process is also that it actually preferentially put it up to the higher excited state. And this is the proposed mechanism. Basically, after we excite the polariton, well, upper polariton would just jump into the first excited state of dark mode, but the lower polariton instead would actually promote the vibrational mode into even higher energy levels. Could be vibrational energy 2, 3, 4, and so on and so forth. We don't really know, but definitely higher than 1. As a result, we still have a ground state bleach. We don't have a lot of population here, right? So what we see, but without this excited state absorption, then what we would expect to see is this purely Rabi splitting contraction, as I showed you here in the simulation, and this is what we see. It's purely symmetric derivative shape. And then as time goes on, the vibrational mode would actually relax back down from the second and third excited state to the first excited state, and then trigger this 1 to 2 transition show up again, and that's how we see this growth of this strong absorption peak. Till the time about 16 picosecond, this relaxation is finished, and then you see this saturated transient absorption peak. But I want to, so we call this hot vibrational dynamics for a reason that you see momentarily. But I also want to say this hot vibrational dynamics is solvent dependent. All the experiments I showed you before are done in hexane. If we switch to toluene, and there's another solvent, I think it's acetone, then we find neither of the upper or lower proton actually would transfer to higher vibrational mode. They would just transfer directly to the first excited state and then down. Okay? So this is still ongoing research, but I want to draw an analogy between the hot vibrational dynamics in proton and the hot electron dynamics in plasma. In hot electron dynamics of plasma, many of you are familiar with, which it initially involved a delocalized charge motion in those nanoparticles, and then quickly relax into the hot electron and hole pairs inside of the particles, which further thermalize into a hot electron hole distribution, and which that can be used for chemical reactions. Okay, so the key is that you generate those hot charge carriers and then have those hot charge carriers to be harvested by some chemical reactions. And here in the proton case, initially we are also creating a delocalized vibrational oscillations. And then this delocalized oscillation, so-called proton, would scattered among each other and then create some very hot individual vibrations among individual molecules, where this hot vibration would also relax within a lifetime of tens of picoseconds into thermalized our first excited vibrational state. So we are hoping that maybe there would be one reaction or two that would allow us to showcase that we can harvest those hot vibrational modes and then trigger some unique chemistry happen using photons. And one of my undergrad, Garrett, is working on it. Okay, so quickly I want to move on to the third phenomenon that we see, that is intermolecular vibrational energy transfer. The idea is that we all know vibrational energy transfer between molecules is hard because the transition, the dipole moment is just so small. It's not like electronic dipole that has a large dipole moment, and dipole-dipole interaction is large. We did a rough calculation that in our system, the efficiency is about 0.1%, so totally negligible. Okay, so we create this model system where we still have our favorite molecule, tungsten hydrogen carbonyl, and its isotope label version, so that they are frequently separate about 40 wave number. We can resolve them in the 2DR and the linear spectrum. We conduct 2DR spectrum. Here is the 2D spectrum. You see the diagonal peak. We also see the diagonal peak of the overtone peak. All right. But what is important is there's nothing here. This is, remember, the cartoon that I showed you. If we have any energy exchange or coupling, we would expect to see cross peak here between the corner drawn by those two lines. There's nothing. So that basically also agrees there's no energy transfer between those two types of molecules. The idea is what's going to happen if we actually put them inside of a cavity. By putting them inside a cavity, there are a few advantages. One is now they would all couple to the same media that is a cavity. Therefore, by exchanging photons, maybe photon would act as a messenger to relay the energy between them. And second, that we also can create some intermediate states like middle protons act as a funnel for energy transfer. But anyway, we believe, or there are belief in the community saying that maybe this is a way to actually relay energy among molecules, like how we talk to each other now through wireless cell phones. All right. So we create this system by having a equimolar of those mixtures and then put them into the same cavity. By doing that, we form a 3-proton system where that we have this upper proton that is mostly composed by the Tungsten-Heisenberg vibrational mode, and the lower proton composed by the isotope labeled version of it. So what we need to see in the 2D spectrum is we want to see if we can see a crossfit between the upper proton and lower proton. If we see that, boom, there is energy transfer. So I'm just going to give you the summary of this result, and this is what it looked like. Okay, so this is the control experiment I showed you before in this data that we are pumping at the upper proton frequency. But then after waiting for a certain amount of time, we see this cross peak show up at lower frequency side that correspond to the lower proton. So that indicates that we definitely have an energy transfer by pumping into this molecule mostly, and then later it transfers its vibrational energy into its isotope labeled version of it. So far that we know that this is the first time that this has been demonstrated. Lastly, I want to show you this intercavity nonlinear interaction between protons. So that is basically the idea, just flip the role of cavity and molecules. What I showed you before is I can actually use a cavity to couple two molecules or two different molecular vibrations together. Then I ask, can I actually let two cavities who do not talk to each other to couple to each other or talk to each other by having them talk to the same vibrational mode? All right? And this is actually important because photons are notoriously for nonlinear interaction. They basically, you have two photons cross each other, they don't talk. They don't see each other for a million years. Okay? So if I can achieve that, this could also be a roadblock for new platform for quantum simulation, for information propagation, for communication type of applications. So to test this idea, my student Jiaxi basically designed and fabricate this type of cavity optics, where it is a checkerboard that we have two types of cavity, A and B. For A and B, for cavity B, it has a slightly higher step compared to cavity A. So when we assemble this cavity with a regular reflective cavity mirror, we can form two types of cavity mode that has slightly different cavity thickness. Okay? So what that allows us to do is within the same setup, we can have two cavity modes, cavity A and cavity B, adjacent to each other. The idea is those cavity modes are wave functions as well. We hope that they will be delocalized, and therefore this delocalization would enable them to talk to each other through coupling to the same type of molecule. So we put molecule in. By putting molecule in, we see this double peak split into 4 peaks. So why 4 peaks? Remember, if we have one cavity mode and one molecule mode, we form a pair of proton. So that's 2 proton peaks. Now I have 4 peaks. That means 2 pair of protons. So the way to explain it is, although I only put one type of vibrational mode in, those vibrational modes actually split into 2 sub-ensembles, where one sub-ensemble would only couple to cavity 1, and the other would couple to cavity A and cavity B. So each of them form 2 protons, and then here that we have protons for cavity A and protons for cavity B. Okay? So when we first realized this is a little bit disheartening because this indicates that they don't actually couple to the same vibrational mode. All right? So, but we further examined these models to see if it's absolutely right. What we did is we did some numerical simulation based on the model I just showed you before. In the model I showed you before, it's basically equivalent to I have 2 types of cavity. There's no talk between each other. Photon comes in cavity A, leave cavity A without going to cavity B. Or photon come to cavity B and leave on the other side of cavity B without talking to cavity A. Okay? By doing this, by using this model and the available equations, we can simulate the result. As you can see, this dashed line here. We can simulate the peak position of the experimental data pretty well, but we can never actually get the peak intensity well enough. And that bothers us for a long time. We just don't think it's good enough. Until one day we realize the fact that there is a intensity difference there might indicate there is some type of coupling between the 2 cavities so that one cavity can borrow some strength from the other cavity. So we change the model and make it to be model 2. In this model 2, it works the following way. We can allow the cavity photon transfer from one cavity to the other. For example, if the photon enters from the cavity A side, it would bounce a few times in cavity A, and then transfer to cavity B, and then bounce a few times, and then leave on the cavity B side. And this is the delocalization we allowed it to do. So we derive this whole equation because it's not available, but after we derive this equation, we can actually fit our experiment really, really well to match not only the peak position and also the intensities. So the take-home message here is delocalization even for linear spectrum matter. We further move on to 2DR to see if we can actually see this nonlinear coupling between cavities that we're craving for. So here is the control result of a uncoupled dual cavity, the 2DR spectrum, and this is the coupled dual cavity. The spectrum looks a little bit messy, but let me go through with you. So in a typical 2DR experiment for a polariton, you expect to see this box feature formed by 4 peaks, right? So we can draw those box features here as one box and another box. Okay, and remember we have 2 pairs of polaritons, so we expect to have 2 pairs of boxes. So that's exactly what we see. But importantly, there's no actual peaks that is not on the corner of those boxes. So it's a clean control experiment. Spectrum become very much messier when it comes to the coupled cavity mode. We can still draw those 2 boxes representing the 2 pairs of polaritons, but there are also unexpected peaks. They are small, but very reproducible, and in those positions that is not on the corner of those boxes. Okay, and they become more clear if we take cut, spectral cut on the 2D spectrum. Here I showed you 2 cuts. One is cut at upper polariton of cavity A, and the other is cut at lower polariton of cavity A. In both cases, we see this very clear cross peak. And this cross peak happened at the frequency of upper polariton from cavity B. Okay? So what it means is by exciting polariton in cavity A, somehow the polariton in cavity B feel this excitation and its optical response actually respond to it. Okay? We can further conduct some simulation to understand to confirm it and understand its origin based on our developed model. So the blue trace is the experimental data. The red trace is the theory simulation. You can see they actually match pretty well. And then from the theory, what we can do is we can decompose the nonlinear contribution from either cavity A or cavity B. And clearly you can see this cross peak is actually coming from the nonlinear response from cavity B. And this is a cut of lower polariton from cavity A. So that again shows that by putting energy into cavity A, I successfully actually perturb the polaritons in cavity B, which is on its neighbor. It's not too far away, but still spatially separated. Okay? We further did the simulation by either turn off delocalization by not allowing photon going cross-border from one side to the other, or by just setting the molecule without any nonlinearity by making it to be purely harmonic. In both cases, we cannot reproduce the observed nonlinear signal, right? One is just a flat line because without nonlinearity, there's no nonlinear signal, and the other one is without the delocalization, we just get a single polariton type of responses. So the key is that it is important to have both cavity delocalization and molecular nonlinearity coexist in the system so that we can reach this intercavity nonlinearity. And it's summarized by this cartoon here. In this cavity, we have 2 cavity modes, where this 2 cavity mode has a certain amount of volume overlap between them. And in this volume overlap, we need to make sure there is some molecule in between them. So those are actually the media that enable the nonlinear talk between those 2 cavities. So I talked a lot about polaritons, but this is only the first part of my talk, but 2/3 of it, okay? So I hope that I showed you really polariton by hybridizing those photon and molecule together, we can achieve a lot from it new and expected, including all 4 of them, and at least some possible applications, mostly in the ultra-fast photonic application, and also some chemistry, you can say is crazy chemistry from a PChem, but we'll try to see if some of them can be realized in the next few years. Now I want to switch gear to talk another side, which is probably more realistic, that is about using SFG microscope to study interfaces of self-assembled materials. So we are interested in self-assembled materials. Like I give you 2 examples. One is metal organic frameworks, MOFs. Those are materials that is, by the way, this is a project led by my student Hao Yuan and also Jackson. Okay, so MOFs has been shown to be very useful because they just have a really large pore size that you can basically put whatever into it, and they are highly functionalizable. One example is that they can actually take up water and be really efficient at it, and probably also candidates for water purification. Okay, the other example, which I'm actually is going to be my focus today, is the cyclodextrin-based host gas self-assembled materials. And those materials are basically composed by 1 quantity of self-assembled of sodium didacryl sulfide and 2 quantity of beta-cyclodextrin. The 3 of them together would form this fundamental unit where Coulombic interaction or hydrogen bond would allow them to form this dimer and further assemble into a nanosheath, and sometimes can be tubular and can be vesicles as well. It really depends on the details, like the salt that you add to it and the concentration. Okay, this material has been proposed and shown to be a responsive material for responsive molecular devices by basically because its morphology can actually change by tuning RH or temperature. And also beta-cyclodextrin itself have been shown to be a good water purification materials. Okay, and all those responses, like response to RH and also water purification, rely on the water-host interaction right at the interface of self-assemblies. And this is actually why that we are interested in the interface of those self-assemblies, so as MOFs as well, because when it uptake water, the important step is first capture the water around the first layer, and once you capture those water, turn it into hydrophilic, then you can capture more and more. So when it's come to interfaces, in our group, we think about SFG spectroscopy. This is a well-known technique to probe interfaces. It's a second-order nonlinear spectroscopy where we send in an infrared pulse to excite a vibrational excitation of molecule, and then this vibrational coherence would subsequently excited by a visible pulse to a virtual state that subsequently would emit the signal at the sum frequency of both incoming beams. That's why it's called sum frequency. It's a second-order nonlinear process. And by definition, second nonlinear order process would only exist in any non-central symmetric media. That include flat interface, like the interface between air and this rock here would be one example. Okay, and therefore it has been studied a lot on flat interfaces like air-water interfaces, solid-solid interfaces, and air-solid interfaces. It is also useful because of this infrared pulse, because it can reach to vibrational fingerprints of molecules. So it's kind of molecular specific. But when it comes to study interfaces of MOFs of this type of self-assembled, it's actually very different because the interface is not flat at all here we talk about. The interface we talk about are basically determined by the morphology of those materials. In the case of MOF, it's actually the interior of this ball. So there's nothing about flat there. So it's a question about whether it's going to work or not. I'm going to say that there's a chance it's going to work because some of the MOFs, at least, and also the self-assembled material I'm going to show today, have inversion symmetry. And remember, aside from interfaces, the other thing SFG would give you signal are just non-central symmetric crystals. Okay? So I would say if the system would meet these 3 criteria, we will still be able to study their interface. The first one is the skeleton of the material cannot have an inversion symmetry. In the case of the beta-CD self-assembly, it doesn't have a mirror plane along XY and doesn't have a C2 rotation axis along Z. That guarantees it doesn't have an inversion symmetry. So good. The SFG skeleton, the self-assembly skeleton should have SFG signal. Okay, and then you say, but you are probing the bulk. However, those materials, so as mouths and many other materials, they are porous, and the bulk is or the body is just the interface. So in that case, every single atom is exposed to the surrounding. They are all interfaces, so it doesn't matter. Lastly, we need a probe molecule actually can tell us we are actually probing those interfaces. And in this case, we are hoping that water molecule, if it can actually strongly absorb onto the skeleton of the beta CD self-assembly, then the water molecule can act as a probe molecule to probe those interfaces. Okay, so this is a similar idea in some of the X-ray crystallography. Water molecule can be seen because they are basically strongly bonded to the protein structures and be part of, be part of the structure. Okay, so now the first challenge is solved. I come to the second challenge. Second challenge is the size of the self-assembly is only on the order of 10 micron size, which is much smaller than the beam size of our SFG spectrometer, 100 micron. So that means that we're going to miss the individual alignment and the orientation of the self-assembly, but see an ensemble average result. But not only that, we might get some misguided result as well. Of course, the way to solve this is just by focusing the beam harder and tighter. And we do that by basically sending our SFG beams into a Schwarzschild objective. Let me go through and therefore building this SFG microscope. Let me go through this setup with you. We have our infrared pulse and the up conversion pulse combined by a dichroic optics, and then sending both beams through the Schwarzschild reflected objective by a mirror, reach to the sample would generate a signal would be reflected back by the same objective, and then collected and sent into the detector. Okay, and then we can scan our stage, and we can also scan the mirror to basically get an image of the sample, so it's a scanning setup. So here is a test that we made this gallium arsenide and gold pattern, and this is the SFG image. You can see we can capture most of the details like the corner, curved corner, stuff like that. The resolution is not so great, 1.5 micron, but it's totally limited by this objective, so we can improve that. But it's good enough for our current purpose with the time resolution about 70 femtoseconds. So with this setup, we went ahead to study the self-assembly. Excuse me. Here I showed you is the SFG intensity image by focusing on the CH modes in this beta cyclodextrin. Okay, so we basically measure the CH SFG response and then sum the SFG intensity together, just plot the SFG intensity as a function of space and position. You can see those bright positions, those correspond to the domains that actually are ordered and then therefore give SFG signal. But behind this image, each of those pixels actually correspond one of those spectrum that I showed you here. So we can also run a code to compare and sort out those pixels based on their spectral similarity that I plotted here. I call it spectral image. And you can see within domains, there are actually spectral similarity between the between pixels, whereas across domains that the spectral can be very different. And mostly it's dominated by two types of domains. One is this green curve, one is this orange curve. They look very similar, but out of phase. In SFG, if they are out of phase, it means they have different orientations on the, on the substrate. Okay? So the most interesting result, I believe, is to do a numerical simulation by summing over this entire area and see how the signal look like. The signal look like this cyan curve here that I showed you. So it's very much smaller compared to even the SFG signal from a single pixel. Why is that the case? Because the SFG are out of phase, and then when you sum them together, of course, they canceled out. That's the numerical explanation. But physically, it also has an explanation. Okay? In order to have SFG has a signal, the molecular species has to sort of ordered. So they need to basically share the same type of alignments. Okay? From the image, we see that the alignments actually exist, but only on the order of tens of microns, right, within the domain of each self-assembly. But overall, on the spatial range of 60 micron, it is not. It's totally disordered. So that means what we are studying is actually self-assemblies that has a local ordering, but on the larger spatial scale, it's not ordered at all. And if we use ensemble average spectroscopy, this ordering would be missed, and we could lead to some misguided conclusions. So now, knowing what we are capable of, we now extend our spectral range from the CH all the way to the OH. And here is a spectral image, an intensity image, and we labeled a few different domains with their represented old age spectrum here. As you can see, the spectrum look different. Some of them has a dominant 1 peak, some of them have 2 peaks, or even 3 peaks. So the spectrum itself is very complicated. I show you one of them. We need to actually understand it by doing a spectral fitting. So we find we need to fit the spectrum by majority 6 peaks, sometimes with a small 7th peak. Whereas 3 of them basically come from CH. So we are not interested in that because we are interested in water interactions. Where the rest of 3, starting from 3,000 wave number all the way to 3,400 wave number, are 3 OH peaks. Okay? And the question is, what are those OH peaks? Beta cyclodextrin has 2 hydroxyl groups. One is called primary OH, the other one is called secondary OH. So basically, we have an additional peak. We want to know, it should come from water, but we want to know which one actually coming from water. To understand it, we basically do this experiment by dry iron purging our sample, or by doing a H2O and D2O exchange. By doing that, we basically want to remove H2O from the sample, and then we want to see which peak would first disappear. In both cases, we see this lower frequency peak disappear first. That leads us to conclude it is a lower frequency that corresponds to the absorbed water, whereas the other peaks, the other 2 peaks must come from beta cyclodextrin. The other interesting thing that we found is on the course of we dry our sample, we found the ratio between the secondary OH and the primary OH actually also increased, which we also use it as an indication for the local hydration levels. So now come back to the spectral assignment. We assign the lowest frequency to be the strongly bonded OH, the middle peak to be the secondary OH, because secondary OH is, has been shown to form hydrogen bond between both water and the secondary OH, as well as with other secondary OH. Whereas the highest frequency peak corresponds to the primary OH on the outside of those dimers that do not actually form any hydrogen bond. That's why it's on the highest frequency side. But the question is now, we see a water signal. I showed you before, only the cyclodextrin actually has the chirality and non-symmetry, non-central symmetry there that will be SFG sensitive. Why water will be SFG sensitive? Water here is just like a water absorbed by a sponge. It's like bulk water, and bulk water is isotropic. It definitely have an inversion center. It wouldn't be SFG active. And the only way that water could be active here is by basically it's absorbed onto specific site in this skeleton, and therefore adapt the same symmetry and the chirality of the skeleton, and then become SFG active. So around the same time, there are a few other groups from Yale and Cornell also observe the same type of effect. So now I want to just go back to the spectral image that I showed you before, where we observe 2 types of spectral shapes. One is with a dominant primary OH peak, the other one with a dominant secondary OH peak. And remember, whenever secondary OH become big, we think it has lower local hydrations compared to the one that secondary OH is small. So what we conclude from those pictures is different self-assembly sheets have a slightly different level of hydrations, with some of them have more water absorbed, some of them have less. But if you zoom in into a specific domain, say this one, and then just probe the spectrum at different positions within the same domain, the spectrum actually look very, very similar, indicating a similar type of hydration level. So lastly, I think this is probably second to last slide. Just want to show you we also can do ultra-fast vibrational energy dynamics, and in different domains, their vibrational energy dynamics is very different. This data is almost a year old. We're still trying to understand everything about it, but it's just really amazing that we can see how spatially resolve all those dynamics in the self-assembled materials. So to summarize about this part, that I showed you that local ordering sometimes exists in self-assembled material, but they are very, very small and can be missed if you use ensemble average measurement. And second, that I showed you a way to generalize SFG to study some more complicated interface, not the interface of a flat interface, because there's a lot of interface that is more interesting than a flat interface, I believe. It needs some criteria. It needs a probe molecule to be templated by the self-assembly, and also need the self-assembly itself to be porous and also non-central symmetric. But I'm going to say there are actually a lot of those material like that. So I show you two other examples using the same technique. We already move on to start to study one type of mouse. This is ZIF90. ZIF90 has a non-centric symmetry there, and it's SFG active. And when we actually put D2O to absorb, we actually definitely see spectral response. Okay, this is just some early preliminary data. We even moved on to some biological samples. That is collagen here. Okay, collagen is the primary protein in our body and in many animals' body, and you can buy them from Costco as well, actually. So we took SFG image in both CH regime and OH regime, and two types of collagen. One is the untreated collagen. The other one is cross-linked collagen, and just see how the spectrum how the image are different. Okay, in the pristine collagen, both CH excuse me, and OH image basically reflect the same type of morphology. Those are tilted lines indicating the collagen fibers. Okay. However, if we cross-linked it, this is the over cross-link, like the stuff that you find from a cancer tumor, then the CH and OH image are not correlated, and everything become large domains and uncharacterized. So we're hoping that this would lead us, by further studying this, would lead us either some molecular signatures to see identify over cross-linked collagen, as well as learning some molecular details about how those cross-linked collagen happen, therefore to contribute to diseases like fibrosis and also cancer metastasis. All right, so now I finally finished, and I want to thank the people who actually contributed and do this work. This is it's a little bit outdated group member, because you see this is Dr. Jiaxi and this is Dr. Yingmin. Both folks have already graduated from the group and move on to their new career. I didn't get time to talk about Wenfan's work, but he's doing some really great work. Bob talked about X-ray, so we're also doing transient X-ray absorptions. And Stacy has been working on our case project, taking over from Yingmin. And Oliver is a exchange student, have been here for the summer and already contributed a lot. Also want to thank about new members, and also Garrett, who's the new undergraduate, has already contributed to the group on those hot vibrational chemistry. All right. Also former postdocs, Daolin Zhiguo and Sri Hart, actually contributed to the project to various levels. Before I forgot, I want to thank actually UCSD first to give me this opportunity, and then it's like a seed grant, and then triggered all the other interesting activities by different agencies, NSF, Air Force, DARPA, DOD, and also CASE, our own CASE. I'm very proud of it, and Air Force, this is Army, also Genentech. I want to thank about many people that I listed as collaborator, more than collaborator. First of all, Bob. Believe it or not, I still remember the first call that you gave me. I was like, I never actually answer any number that I don't know, but for some reason I answered this one, and there's a really energetic man say, hey, this is Wei Xiong. I'm Bob Continetti from UCSD. I was like, what's going on here? Something good? All right, so that is the beginning of the journey. I really want to thank you that hired me 5 years ago and give me this great opportunity. I hope that I live up to your expectation. And also, we have a collaboration. We eventually, hopefully, going to combine your instrument and my instrument together for case. I want to thank Vicky. Vicky came in. I didn't know how your hiring is important to me before you came, after you came. And it's become really, really important for both my academic and personal life, I really want to thank you for all the support that you give me. I want to thank Francesco, who's unfortunately not here. He's been a great collaborator and also great mentor starting from very beginning. And Kim Priester for her support on using case, support on case, and also many guidance. Howell has been a great collaborator on the Proton project. Always, he's the first layer of reviewer, I would say. We have something sent it to him and his crew, and then they give us a lot of feedback that, hey, you got to fix this and this and that. And from a theoretical point of view, it's very different. I think we're coming from different planets. And then special thanks for Raphael, who's basically the driving force. Raphael is the postdoc from Howell School, but without you, I think the collaboration would not run as smooth as we can, fruitful as we can now. I want to thank Adam, Jeff, and Blake from NRL who introduced and the Proton, Proton topics into my lab and really become a really wonderful journey in my lab. I want to thank Cliff. Cliff, you gave me the early sample that I had in my career, and definitely super duper important for me. We're still measuring samples for you guys and learning really interesting stuff. We have actually some data we haven't read up yet, by the way. Same as Josh, we are measuring your second batch of sample, but we haven't worked on the data we collected 3 years ago. So let's work on that. I want to thank Shirley, who actually collaborated with us on some other project. My friends Anne from Genentech on a protein project that we work with. I want to thank a lot of friends from PAE section and department. I couldn't list everyone, but Judy and Mike, you guys just have been great mentors and great friends that encouraged me all the way in 5 years. I definitely don't think the 5 years is long at all because I have a lot of support from you guys and it doesn't make me suffer too much. I want to thank Amit and Andy to be the leadership in our section, and there's a great way to go. And finally, I want to give a special shout out to my partner or my husband, Difo. So it's been 13 years since we met in college in Beijing. And so back then, nobody would believe when a young kid say they want to be a professor in the US in a top institute. They just think that you're daydreaming. I don't know if he believed or not, but he actually supported me all the way for 13 years, from Beijing, Wisconsin, Colorado, and now at San Diego. So it's really a great journey, and without him, I don't think I can do it. Unfortunately, he can't be here because he's working in Albuquerque now, but I really want to thank him. And some of you, if you see him, make sure that I acknowledge him. All right, so with that, I'm open to questions.
One quick question, and the students can come back to me if we run out. But the mixed isotope one where you had the coupling, the snapshot you showed was at 30 picoseconds, and I thought that was several times longer than the dephasing time, the 5 or 6. How does that happen?
Yeah, I took out the dynamics data that we collected. Basically, excuse me. The cross-peak saturated around 5 picoseconds. So the exchange stopped at 5 picoseconds. It is just for some reason Nicolas Bohr, but he really likes 30 picosecond data. So he always plot his 30 picosecond data out. But really the energy transfer finished at 5 picoseconds.
With molecular vibrational polaritons, you talked about energy transfer, quantum information, and communications. What about good old chemical reactions? Have you seen any bond breaking?
Well, we tried one with tungsten hexcarbonyl. It didn't work, so we are moving on to other molecules. So I think what is important is basically finding the right coordinate break, right? So with tungsten high carbonyl, what we want to break is a is tungsten and carbonyl bond. But what very exciting is the carbonyl and the carbonyl bond, CO bond, right? So the energy would not sufficiently actually transfer to the other bond. But Garrett, my undergrad, has actually searched through a library, and we found some. Oh my God, I forgot the reaction, but some reaction involve carbonyls, and we're gonna try it and see if it's gonna work. I have talked to Valerie once, and I'm gonna probably go back to you again, talk to you, see if there's any reaction that could work. But the key is basically if there is a reaction that breaking one certain bond is important, and we can actually strongly couple to this bond, I do believe it's gonna work. It's not gonna work for every cases, but some cases.
Can you give a simple explanation? You spoke about two cavities coupled through the vibration, and you had to develop two different models. Why presence of one vibration talking to both cavities is not enough to explain it?
Sorry, say that again?
Why simply presence of one vibration coupled to two cavity modes is not enough to explain it?
Oh, good question. Because my two cavity modes are spatially separated, right? So those are like basically two rooms. Imagine that we have divided this entire room into two. My molecule, as each molecule are still individual molecule, right? In order to actually have the two cavities to talk to each other, they have to talk to the same molecule, same individual molecule. I cannot have the same individual molecule to be present in both room A and room B. The only way I can is I can have this molecule to sit in the border where then both cavity can talk to it. That's at least what we believe happened.
Yes, you.
Maybe this is kind of impractical, but you said that in the first set of projects, you need a molecule in the overlap of the two cavity modes to see the coupling. Would that constitute like molecules in the overlap versus not in the overlap? Would that be enough of an interface to be able to look at that with SFG?
Good question. We're not thinking about SFG, but what we're trying to do is doing I didn't say this cavity is not small. It's like 50 micron size. Excuse me. 50 micron size. So even with infrared pulse, we can actually image it. So what I want to do next is actually to image those protons and actually see it from an image by putting energy into one cavity, the other cavity actually respond. Especially I'm expecting that it's the boundary layer that's gonna respond, not the entire thing. But then down the road, what I'm thinking is like, then how can we actually transport this energy further? Like guiding the energy for example, for information communication type of applications.
All right, Misha, round two.
One more question. You saw this nice example where you have increase of the signal with decrease of number of molecules. If I simply stupidly go and decrease them further, at some point I should start probably losing the signal. What is the physics? Because your explanation only gives you some hint why signal increases with the number of molecules goes down.
I don't lose the signal if I
You don't.
use. I mean, if I can do this experiment by constantly shrinking my cavity size, and then also reducing the number of molecules inside, and then eventually reach to this limit that the cavity only has one molecule. Then I reach to this truly single molecule, single cavity strong coupling regime. In this case, by shooting one photon in, I just shut up the entire interaction with the following photons. Because I'm going to excite this molecule into the excited state, it will become transparent to the cavity, basically. So that is the extreme of nonlinearity. You turn on and turn off the interaction by just one photon. And people actually have shown that only in cases like reverb atom, huge orbitals, and then quantum dots, stuff like that, where they can build a so-called pico cavity and then put one single molecule there. But the quick answer is, by actually further reducing it, you're going to expect to reach even higher and higher of nonlinearity. And there are some follow-up experiments my student want to do and then show that. We don't know exactly what is our limitation. We definitely are not capable to do any nanopico cavities, but in the future.
One more, Mike.
Sort of relates a little bit to what I wanted to ask about the saturation and the mechanism of saturation. Is that, what's the ratio of the photon count per unit, whatever, relaxation time, and the number of molecules? Is it the shift, or is it the loss of the, is it the shifting mechanism that saturates, or is it just too many excited states that you've depleted?
That's a really good question. So we actually modeled the data, and this is the interesting part about it. I'm not claiming that I completely understand it. Let me see if I have backup slide actually to show you this. This is a backup slide. So this is the modeling that we did here. This is backup. This is the model. This is the type of signal that we see, right? So in the modeling, we basically have an equation, right? And then this equation is just the regular equation people use to model fiber pore cavity. We have two parameters we can change. One is the amplitude of the absorption, which is represent to populations of molecules inside. One is the line width of the transition. So typically, if you do a pump probe experiment, you will think that what you excite is actually remove population from one side to the other. So we change the population. But when we change the population, we get this derivative of line shape. So that, because it's causing this rapid splitting contraction, as I explained before. So it's not representing this objective signal at all, right? However, then I have nothing to change but other than the line width. So I just change the line width. When we change the line width, we find that it actually can reproduce this objective line shape. So what we believe happened is actually, by reaching to saturation, we somehow actually change the dephasing mechanism and then make the line width become, I believe this case is broader. So it dephase faster and then generating this signal. So this is why you remember that the signal is actually correlated to the coherence other than the population, and this is also consistent with this data. It's purely a coherence effect. Why it leads to the saturation and everything leads it to the fast dephasing, we have some hypothesis there, but just microscopically we don't know. I think unless someone can do a atomic level of simulations. Yeah. But really good question.
All right, well, let's thank Wei for
Yeah.
powered through.
Yeah, actually it's better towards the end.